So let's talk about local extrema. Okay, and an extremum is basically a minimum or maximum. So another word for local extrema, we could have said local minima and maxima. It's just easier to just say local extrema, which encompasses both of those concepts. Now, functions of one variable have local extrema. The tops of peaks are the local maxes, and the bottoms of crests are the local minima. Something to notice here is that a slope at local extrema is 0. So if we had the slope over here, you'd have a slope that's just flat, okay? So you have a 0 slope at the local extrema. The derivative there is 0 for functions of one variable. So another way of saying that the slope is 0 is that f prime equals 0 at the x's that would correspond to where the local extrema are. So what does the local part mean in local extrema? Well, consider this point here. It's a local min. Does that mean that it's the lowest point of the function? No, I mean this point here is even lower than it. But what it does mean is that it's the lowest point in a neighborhood around it. Okay, so if you look at the points around that local min, they're higher than this point here. So it's at the bottom of a crest. That doesn't mean it has to be the bottom of the whole function. Okay, when we discuss the lowest point of a function in a given set or domain, then that's the topic of absolute extrema. Okay, for now we're just looking for the local extrema. So how do local extrema look for functions of two variables? Well, here we have the graph of a function of two variables, and you can see that the local maxima are located at the top of the hill, right? Top of the peak. And the local minima are at the bottom of, let's call it a crater, okay? So these are local minima. You see here two different local minima, and you see two different local maxima. And we also remind you of that distinction that the local max doesn't necessarily have to be the highest point of the function in a region, but locally it is the highest point. It's higher than the points around it, higher or equal in height to the points around it. So how to find these local extrema in a setting where we're dealing with functions of two variables? Well, this theorem is going to help us. If f has a local max or min at the point AB, and the partial derivatives exist at the point AB, then the partial derivatives are 0 at that point AB. Both partial derivatives are 0, okay? Both the partial derivative with respect to x and the partial derivative with respect to y simultaneously have to be 0 at the point AB. The analog to that in a setting of a function of one variable is the fact that the slopes are 0. So the derivative at a point where there's a local min or local max, the derivative is 0 there. Now, focusing a little bit on the one variable situation, you might recall that if at a point x the derivative is 0, that's no guarantee that there's a local min or max there. The quintessential example there is the function of one variable x cubed. Okay? If you take the derivative of x cubed, you'll get 2x. And so what's the value of the derivative at the origin? At x equals 0, it's 0. So here you have the derivative being equal to 0 at the origin, but clearly that's not a local max or min. An analogous situation occurs with functions of two variables where you could get these things called saddle points. Okay, here both partial derivatives will be equal to 0, but they are not local extrema. And here is a visualization of a point where you could have both partial derivatives being equal to 0, yet you do not have a local extrema. So take a look at the graph of this function. At the origin there, the partial derivatives are 0, but the function at the origin is neither a local max or a local min. So we have to be careful when we deal with points where the partial derivatives are 0. It's not a guarantee of local max or min. And you also get to see why we call those points saddle points, because you get the graph of the function looks like a saddle around that point. But still, all hope is not lost. Where the both partial derivatives are 0, provide candidates, at least for local extrema. What we could do is see where the partial derivatives are 0, and then take a closer look at whether there's a local max and local min, and we'll use the second derivative test to classify those points. So all hope is not lost, and this theorem indeed is useful because it at least gives us candidates. Moreover, points where the partial derivatives don't exist also need closer attention. I mean, considering functions of one variable, for example, you could get a cusp where the derivative doesn't exist at the top of that cusp, but it's still a max. So what do we learn at the end by this theorem? That places where the derivatives are 0 and places where the derivatives don't exist should be taken a closer look at for candidates for our local extrema. And because these points are important, we give them a name. We call them critical points. Okay, so what's a critical point? It's a point of the function where either both partial derivatives exist simultaneously. Notice they're both at AB and both partial derivatives are 0. Or at least one of the partial derivatives does not exist, which may give us a situation of a cusp. So those are called critical points, and those critical points are going to give us the candidates for our local extrema. So let's take a look at a concrete example. We want to find the critical points of this function here. Okay. Now, this function f is differentiable everywhere. Clearly, there's no complication, some place where the partial derivative might not exist. So we know that we won't be getting critical points of the category where one of the partial derivatives does not exist. So we're left with dealing with the other category, which is where the partial derivatives exist and are simultaneously equal to 0. So let's start looking for these critical points. So we'll take the partial derivative with respect to x and then set it equal to 0. And we get all of these different possible solutions. That y equals 0, and that's a line. Okay, here's the line y equals 0. You could get x equal to 1. That's the line over here. And y equals minus 3. That's the line in the plane that you see there. What is significant about the blue that you see in this graph? Anywhere along the blue lines, that's a place where the function's partial derivative with respect to x equals 0. Now, we got very simple lines, but in principle, this could have been much more complicated. I mean, we could have gotten all sorts of curves and different geometrical shapes, but this is a very simple example, and we only get the straight lines for the where the partial derivative with respect to x equals 0. Now we could do a similar thing with the partial derivative with respect to y, set it equal to 0, and we get all of these different possible solutions. There are also lines in the plane. Okay, and what's significant about the green line in the plane there? Those are lines in the domain at which the partial derivative with respect to y equals 0. Okay? Now, what's a critical point? A critical point is where both partial derivatives are equal to 0 simultaneously. So graphically, that's where the green and blue intersect. Okay? So I have these circled in red around here. That is where your green lines and your blue lines intersect. And again, this could be more complicated than these simple lines. But for our example, it is that simple. And so we try to solve for where both of these partial derivatives are simultaneously 0. Although you could read off the critical points by the graph here, that doesn't give us a very practical way of computing them for more complicated situations. For that, what we could do is the following. So we take a solution where we know the partial derivative equals 0. That's the line y equals 0 here. Okay? So I'm going to take the line y equals 0, and I'm going to take that solution and plug it into the equation where the partial derivative with respect to y equals 0. Doing that, you see here in green basically is where, is the equation above, and in blue I have y equals 0 because I'm plugging in that solution. So I plug that in and I get x equals 0 or x equals 2. What the heck did that mean? Well, as I'm moving along the solution y equals 0, okay, I'm going to intersect at two different places where also fy equals 0. And that happens to be the place x equals 0 there and x equals 2 here. And so what I get is these two critical points. The x is equal to 0 and the x is equal to 2. And now both of these have y equal to 0 in them. And why is that? Because I already chose to plug in the y equals 0 solution. So I know the y has to be 0. Continuing on like this, so let's take the x equals 1 solution for the partial derivative with respect to x equals 0 equation and plug it in. So here we have the 1 that corresponds to that x, and 1 corresponds to that x, and y is just left alone, and we have this equation. We solve and we get y equals minus 3 halves, and that gives us the critical point 1 minus 3 halves. Where did I get the 1? Well, that's where we started with the x equals 1 solution to the first equation. Okay, so here's the x equals 1 solution. I'm moving along that line, and when I plug it in to the second equation, I'm basically asking, where does the blue line intersect any green line? Okay, and we get an intersection at y equals minus 3 halves, and so that's where we get our point 1 minus 3 halves. And finally, we do the same thing with y equals negative 3, plug it into the original equation there, we get x equals 0, and so that provides these two critical points. And so we have a total of 5 critical points. These two, this, and that right there. And again, that's a practical way now to compute the critical points. You take the solutions of one equation and you plug them into the second equation and solve. Okay? And that's the practical way. You can't just do things graphically, looking at them. We can only do that in this example because it's simple. Other examples, it's generally more complicated. And if you want to see how the graph of the function, which we just found the critical points for, looks, here it is. You could see there in red, that's the x equals 1 line. And in blue is the y equals minus 3 half line. And we see that where they intersect, you get a local max there. We could also change this and find another point, say 0, 0, right there. Where they intersect, we get a saddle point. And we'll talk about how to classify these critical points in a future video. And returning back to the previous traces, you could see that along this blue line, everywhere along this blue line, the partial derivative with respect to y is 0. And along the red line, the partial derivative with respect to x is 0. But where they intersect, both partial derivatives are 0, and we actually have a local max there.